Good morning, students.
Good morning, ma'am.
Okay, good morning. So in our previous class, we discussed about the AC voltage through inductor, and we derive an expression for the current that is generating in an inductor when it is connected to an AC voltage source. So what about the equation for calculating the value of current that is developed in a inductor when it is connected to AC voltage source? Dia.
Im sin into omega t minus 90.
I is equal to Im sin omega t 90 sin omega t minus 90. So here we can say that in the case of voltage, same AC voltage source is applied to the inductor. That is V is equal to Vm sin omega t, but the value of current is I is equal to Im sin omega t minus 90. So here from this, we can draw an important conclusion that in the case of inductor, when it is connected to an AC voltage source, the current lags by 90 degree, because here the phase angle is not the same because the current is lags the EMF by 90 degree. So all of you draw that conclusion from here. In the case of inductor, current lags EMF by an angle of 90 degree. In the case of inductor, current lags EMF by an angle of 90 degree. So this is one of the most important result that we are drawn from AC voltage through inductor. In the case of AC voltage through resistor, both the current and voltage are in same phase. But in case of inductor, here the current is lags the EMF by an angle of 90 degree, because in inductor V is equal to Vm sin omega t. Here omega t is the phase angle. The value of current I is equal to Im sin omega t minus 90. So here the phase angle is shifted from 90 degree by an angle of 90 degree. So we can say that current lags EMF by an angle of 90 degree. So here I will give you a short method to remember, because we are discussing another case in the case of a capacitor. So here the E stands for EMF, L for inductor, and I for current. So here E stands for EMF, L for inductor, and I for current. In Malayalam, we can call it as LE, right? So in the case of inductor, current lags EMF. In the case of inductor, current lags EMF, or we can say that EMF leads the current by 90 degree. Okay, and vice versa. In the case of inductor, EMF leads the current by 90 degree, or you can say in the case of inductor, current lags, because here the current is the third term. Current lags EMF by an angle of 90 degree. Okay. So what is our next step? Here we derive an expression for voltage and current. What is our next step? We need to draw the phasor diagram. Before that, graphical representation. So write the heading, graphical representation of AC voltage through inductor. Graphical representation of AC voltage through inductor. So for that, here we consider the phase angle, both in the case of EMF and that of the current. So omega t In the case of EMF, it is V is equal to Vm sin omega t. In the case of current, it is I is equal to Im sin omega t minus 90. And our angle 0 degree, 90 degree. The alternate angles, because alternating current are those current which is varies at alternate intervals or at regular intervals. So 180 degree. What is our next angle? 0, 90, 180. After that, 270. Then 360. So first of all, we can find out the phase angle corresponding to EMF for alternate angles. So first V is equal to Vm sin omega t. The first phase angle is 0 degree. Vm sin omega t. So here omega t is equal to 0. So sin 0 is equal to sin 0. Sin 0, 0. So Vm into sin 0 is equal to 0. So the first angle becomes 0. Again, the next phase angle omega t is equal to 90 degree. V is equal to Vm sin 90. What is sin 90?
1.
1. So Vm into 1 is equal to Vm. Positive Vm plus Vm. The next phase angle is 180 degree. Sin 180 is equal to, yeah, 0. So V is equal to 0. Next one is 270 degree. Sin 270 minus 1. So V is equal to Vm into minus 1 minus Vm or negative Vm. Then the last one 360. Sin 360 is equal to 0. So it becomes 0. Now we can find the values of current for alternate angles. I is equal to Im sin omega t minus 90. So the first angle is 0. So here we need to find sin 0 minus 90 degree. Sin 0 minus 90 degree, that is equal to sin minus 90. What is sin minus 90? What is sin 90? Sin 90 is equal to 1. But here it is minus 90. So we get minus 1, right? So the answer become I is equal to minus Im. So the starting value is negative Im. What about the value of current if the phase angle omega t is equal to 90 degree? If omega t is equal to 90 degree, the value of current become I is equal to Im sin, instead of omega t, we substitute 90. So 90 minus 90. 90 minus 90 is equal to 0. So Im sin 0. What is sin 0? 0. So that term becomes equal to 0. Now the third case, 180 degree. If the phase angle is 180 degree, I is equal to Im sin 180 minus 90.
Sin 90.
Sin 90. Sin 90 is equal to 1. So the value of current become equal to positive Im. The next phase angle is 270 degree. 270 minus 90. I is equal to Im sine 270 minus 90.
What is
180. Then what about sine 180?
0?
0. So that term becomes equal to 0. The last one, 360. I is equal to Im sine 360 minus 90.
270
It is 270. Then what is sine 270?
negative
Negative 1. Sine 270 is equal to negative 1. So I is equal to negative Im. So here we get all the values of the alternative source of EMF, and that for the current for different phase angle or for the alternating phase angle. So here you can write the values. If first angle is equal to 0, if we get the phase angle of the first case, then you can find the alternate cases very easily. So if the first angle is 0, then we can write the alternate angles as equal to 0. Similarly, here, if the first angle is equal to minus Im, we need to find out the alternate cases. Otherwise, the alternate angles are equal to 0. So now we can draw the graph. Along the x-axis, we take the phase angle omega t. And along the y-axis, we have current, the value of current and that of the potential. So we can take Im and Vm. Here we have negative y-axis, negative Im and negative Vm. Mark all the angles and try to draw the graph. 0 degree, 90 degree, 180, 270, 360. So first of all, we can draw the graph corresponding to the value of EMF, Vm. For 0 degree, V is starting from 0. And for 90, it is plus Vm. The first point is starting from here. For 90 degree, it is positive Vm. For 180 degree, what is the value of EMF? Alternative source of voltage? 0. Again, for 270 degree, what about the value of V? Negative Vm. And for 360, it is 0. So now we can join all these points. Similarly, we can draw the graph corresponding to the value of current. And in the case of current, it is starting from negative Im, because for if omega t is equal to 0 degree, the value of corresponding alternating current I is equal to negative Im. So for corresponding to 0 degree, it is starting from here. For 90 degree, it is 0. Then for 180, it is plus Im. For 270, 0. And then for 360, it is 0. So we get a graph like this. Here the solid line is represents the graph corresponding to EMF, and this dotted line represents the graph corresponding to current. This is a graphical representation of AC voltage through inductor. So from the same graph itself, we can draw the value of voltage and that of the current in the case of AC voltage through inductor. Solid line is mainly used to represent the value of EMF, and the dotted line is used to represent the value of current for different phase angles. Is it clear?
Yes.
Okay. Then what about our next step? So here we derive the equation for current. Then we find the graphical representation for AC voltage through inductor. Then what about our next step? Yes, the next one, next case.
Ma'am,
Yes,
can you show previous slide for 1 second?
this tabular form, right?
Yes, ma'am. Ma'am, here for 360 degree we got minus Im, right? So there,
Yes.
how did we plot it to 0?
Okay. It is minus Im, right?
Yes, ma'am.
What about 270? 270, it is 0. And 360, it is minus Im. Yeah. So it stops here. Here we have 360. You only need up to mark up to minus Im, but because the angle corresponding to 360 degree, the value of current is minus Im. So here, you don't need to mark it towards 0. Sorry. Is it over?
Yes,
So
ma'am.
now we are going to discuss about the next step is representation of phasor diagram. Phasor diagram for AC voltage through inductor. What is the use of phasor diagram, students? Phasor diagram. Or what do you mean by phasor diagram?
To represent the phase angle.
Yes, it is used to represent the phase angle with respect to the origin. So this is why we are drawing this phasor diagram corresponding to resistor, inductor, and one more case we need to discuss, that is about the capacitor. So phasor diagram is a diagram that is used to represent the phase angle omega t with respect to the origin. So draw the phase diagram. Here we have 0 degree, 90 degree, 180 degree, 270 degree, and here we have again 360. And we know that in the case of EMF, the value of V is equal to Vm sin omega t. The phase angle is omega t. That is, the phase angle is shifted from an angle of omega t from the origin. So it is shifted by an angle of omega t from the origin. This is for EMF. V is equal to Vm sin omega t. The phase angle is shifted omega t angle from that of the origin. But what about the case of value of current? I is equal to Im sin omega t minus 90. I is equal to Im sin omega t minus 90. That is, the value of current is lags the EMF by an angle of 90 degree. Omega t minus 90. That is, it shifted by an angle omega t minus 90. This is represents I is equal to Im sin omega t. In the case of resistor, both the EMF and that of the current are along the same phase because they possess the same phase angle omega t. But here in the case of inductor, V is equal to Vm sin omega t. So it shifts an angle omega t with respect to the origin. But in the case of value of current, it lags the EMF by an angle of 90 degree. So the phasor diagram will be like this in the case of AC voltage through inductor. Here we need to discuss one more graph in the case of AC voltage through inductor. A special case.
Ma'am,
Yes.
you completed. Ma'am,
Yes.
Now the angle is omega t minus 90, right?
Ah, yeah. Omega t minus 90. Is it over, Achyut?
yes, ma'am.
Okay. Now we have a special case. That is the graphical representation of inductive reactance versus frequency. Graphical representation of inductive reactance versus frequency. Inductive reactance and frequency. Which letter that we are used to represent the inductive reactance? What is inductive reactance? L is inductance. Inductive reactance. Chi L. Chi L is represents the inductive reactance. Inductive reactance is a term that is something equivalent to that of the resistance in the case of a resistor. So inductive reactance means it is the resistance offered by the inductor. That is what is meant by inductive reactance. Okay, chi L is equal to, what is chi L? What is the value of chi L? Equation for calculating this inductive reactance.
L omega.
Chi L is equal to L omega. Okay, but omega is equal to 2 pi f. Angular frequency omega is equal to 2 pi f. So we can write chi L is equal to L into 2 pi f, where L is the inductance, f is the frequency. Chi L is equal to L omega, where L is the inductance, omega is the angular frequency, and the another relation between omega and that of the linear frequency is given by omega is equal to 2 pi f. So chi L is equal to L into 2 pi f. So can you say how this inductive reactance and that of the frequency is related to each other, whether they are directly proportional to each other or indirectly proportional to each other? How this chi L and yes, they are directly proportional to each other. In this equation, all the terms are like in the same line. So we can say that they are directly proportional to each other. That is, whenever the inductive reactance increases, the frequency offered by the inductor is also increases. So the graphical representation will be like this. Here we take the frequency along the x-axis and inductive reactance chi L is taken along the y-axis. And from this equation, it is clear that the term inductive reactance and that of the frequency is directly proportional to each other. So the graph will be a straight line. Whenever the frequency increases, the value of inductive reactance increases and vice versa. Or if the value of inductive reactance increases, the value of frequency that is possessed by the inductor is also increases. This is a special case that is comes under the case of AC voltage through inductor. So here we just make a relation between inductive reactance and that of the frequency. So here we derive the expression for current. Then graphical representation of AC voltage through inductor is over. Then phasor diagram is over. What is our next step? What we want to find out from here? Yeah, we need to calculate the value of power. Okay, so all of you write the next heading. Instantaneous value of power. Instantaneous value of power generated in an inductor when it is connected to AC voltage source. Or you just write the subheading, instantaneous value of power.
Ma'am,
Yes,
in the last page, you have written a few things, right? And then
yes,
what,
Achu.
No, ma'am. Can you explain what you wrote now on the left side? This
So
card.
I am just to summarize all the points that what we are discuss the topics under each category. In the case of resistor, we discuss the value of expression for current. Then we are represent the graphical representation of AC voltage through resistor. Then we draw the phasor diagram. The same thing we are follow in the case of AC voltage through inductor. So here we are deriving the expression for current, that is whenever AC voltage is connected through inductor, and the graphical representation of AC voltage through inductor. And in the previous session, we discussed the phasor diagram corresponding to AC voltage through inductor. Then the next step, we are going to derive an expression for instantaneous value of power that generated in an inductor when it is connected to AC voltage source. I'm just summarize or conclude all the points. That's all. You don't need to copy down it.
Okay, ma'am.
So instantaneous value of power. We know that the general expression for calculating the value of power. What is the general expression for calculating power? P is equal to VI. P is equal to V into I. Product of voltage and current gives the value of power. And here we are calculating instantaneous value of power. So we can write P instantaneous, that is equal to, in the case of AC voltage through inductor, here we are applying an alternative source of EMF. So instead of this V, it is equal to Vm sine omega t, Vm sine omega t. And the value of current that generated in an inductor when an AC voltage source is applied. And students, we know that actually the current is generated in terms of cosine function. Did you remember that case? When we are connecting an AC voltage through an inductor, it will generate a current in terms of cosine function. We get an expression like this: I is equal to minus Im cos omega t. After that, we are converting this cos omega t function in terms of sine omega. So in order to derive the expression for instantaneous value of power, we take this value of current in terms of the cosine function itself. So the current that is generated in the in the inductor when it is connected to an AC voltage is given by minus Im cos omega t. We don't need to write the sine function in terms of sine function. We just write it in terms of the cos function itself. So instantaneous value of power is equal to Vm sine omega t into minus Im cos omega t. Or we can write instantaneous value of power is equal to minus Vm Im sine omega t cos omega t. Actually, the instantaneous value of power, actually the value of current that is generated in an inductor when it is connected to an AC voltage source is given by I is equal to minus Im cos omega t. But we know that the alternating current are represented in terms of sine function. That is why during that time we are converted in terms of sine function, that is sine omega t minus 90. But for the derivation of the instantaneous value of power, we take the actual value that is generated in an inductor when we are connected it to AC voltage source. That is why we take the same value here, I is equal to minus Im cos omega t. So the expression become P instantaneous is equal to minus Vm Im sine omega t cos omega t. Now the next step, multiply and divide the equation by 2. Multiply and divide the equation by 2. Multiply and divide the above equation by 2. Then it becomes instantaneous value of power is equal to P instant is equal to minus Vm Im divided by 2 into 2 into sine omega t cos omega t. Multiply and divide the above equation by 2. So we get P instant is equal to minus Vm Im by 2 into 2 sine omega t cos omega t. Yes, again in trigonometry, what is 2 sine theta cos theta?
Sine 2 theta.
Yes, that is equal to sine 2 theta. Similarly, here we have 2 sine. This expression is 2 sine omega t cos omega t. It becomes
Sine 2 omega t.
sine 2 omega t. So from trigonometry, we have 2 sine theta cos theta is equal to sine theta. Similarly, here we have another phase angle omega t. So 2 sine omega t cos omega t is equal to sine 2 omega t. That is, this term will be equal to sine 2 omega t. So the expression for instantaneous value of power becomes P instant is equal to minus Vm Im divided by 2 into sine 2 omega t. So this is an equation for calculating the instantaneous value of power in the case of AC voltage through inductor. P instant is equal to minus Vm Im divided by 2 into sine 2 omega t. So here we calculate the instantaneous value of power. So we can calculate the next step. We can calculate our after this instantaneous value of power, we can calculate the average value of power. Okay, so write the next heading. Therefore, average value of power is given by average value of power is equal to, it is represented by P bar. So from this above equation, we can calculate the average value. So P bar is equal to minus Vm Im divided by 2, and we need to take the summation of this sine function. That is summation of sine 2 omega t. Average value of power P bar is equal to minus Vm Im by 2 into summation of sine 2 omega t. Again here, the value of sine 2 omega t, average value or the summation of this sine 2 omega t is equal to 0. The average value or the summation of sine 2 omega t is equal to 0. Therefore, the average value of P bar is equal to, the last term becomes equal to 0. Then what about the value of average value of power P bar?
0.
0. So in the case of AC voltage through inductor, the average value of power is equal to 0. So that's all about the average value of AC voltage through inductor. So once again, we can collect all the equations. Now, Rin, what about the value of voltage? In the case of AC voltage through inductor, AC voltage through inductor. What about the value of voltage? Yes. V is equal to Vm sine omega t. V is equal to Vm sine omega t. Sharon, equation for current?
I is equal to Im sin omega t.
Sine omega t. In the case of inductor,
Minus 90 degree.
minus 90 degree. Then Malavika, what about the value of power? Instantaneous value of power. Michael, instantaneous value of power. Emmanuel,
Yes, ma'am.
what about the value of instantaneous value of power?
Vm sin theta. Im cos theta. Ala, omega t.
No. Aditya,
Yes, ma'am. Minus Vm Im by 2
minus Vm Im by 2
sine 2 omega t.
sine 2 omega t. And then Muhammad Adim, average value of power. Nandana, what about the average value of power?
0.
0. So these are the equation that comes under the AC voltage through inductor. Okay, students, with this we can wind up this session.